Okay, so let's begin. So today we are going to discuss about linear stability analysis. Okay, so far what we have seen is there will be a system given in the form of a nonlinear differential equation, a first order nonlinear differential equation, and for this first order nonlinear differential equation, the way we analyze is we plot x dot versus x, and we identify for a given x how the x will evolve. Okay, and that we do by graphical approach. In that graphical approach we identify some points as fixed points. Okay, let me denote that fixed points as x star. And what are those fixed points? At those points my x dot, okay, my x dot, which is f of x star, at those fixed points the x dot will be 0. Okay, and in those fixed points it can be classified into two. One is stable, another one is unstable, right? And how to identify whether it's a stable or unstable? That we can identify using graphical approach again. So if I give a little disturbance, and if it's approaching towards the fixed point, then it's stable, and if it's going away from the fixed point, then it's unstable. Okay, and here what we are going to do is we are going to use a linear stability analysis, which is one of the analytical method in order to identify or in order to classify what kind of fixed point that is. Okay, whether it's stable or unstable. Okay, so how are we going to do that? We are going to do that, but before we do that, I'm going to introduce a parameter such that x, which is equal to x star plus eta. Okay, eta is the parameter which I'm introducing, which is defined in this manner. So what is eta? It is the deviation from the fixed point. That's what it means. Okay, so now what I'm going to do is I'm going to introduce this definition into this equation. This equation. Let me do that. So if I use this, then what do I get? In the place of x dot, I'll put dot of this whole thing, time derivative of this whole thing. So the way I'm going to write is x star plus zeta, the whole dot, which is equal to f of, in the place of x I'm going to put x star plus eta. So x star plus eta. Okay, so now this side, if I derive it further, I'll get x star dot plus eta dot. Okay, which is equal to okay, now this equation I could express it in Taylor series. So if I express that in Taylor series, I will get x star plus eta into f prime of x star, right, and plus some higher order terms. Okay, I'm gonna put that as eta, so it will be in the order of eta square. Fine. Now let's see this one. if I see this one, x star is constant, the fixed point is constant, so this goes to 0, this goes to 0, so my left hand side will be just eta and my right hand side. And what about this one? This will also go to 0, right? This will also go to 0, because that's the definition of fixed point, isn't it? So I will have only this term, and eta of f prime of x star, okay, and plus the higher order term. And if I choose the deviation which are very small, or if I choose the x which is very near to the fixed point, okay, then my eta is very small, so I can ignore this higher order terms. Okay, the omission of this higher order term is valid only if eta is very small. Okay, so in that region, say I omit this term, so finally I will end up with this equation, right? Now so as I said earlier, eta represents the deviation. Okay, so now to understand the stability of the fixed point, we need to see whether this deviation is increasing or decreasing. So if the deviation is decreasing and if it approaches to 0, right, then there is no deviation, so that I could say that particular fixed point is a stable fixed point. Okay, if it's keep on increasing, then it's an unstable fixed point. Okay, now for the further illustration, let me call this f prime of x star as r. Okay, r into eta. Okay, and if I solve this equation, what do I get? That's easy to solve because that's a linear differential equation. So what do I get is eta of t, which is equal to eta naught, which is the initial deviation, into e to the power of rt. Okay, so now if t is very large, okay, if t approaches infinite, what will happen to eta? Whether that deviation will die down or it will keep on increasing, and that depends on the value r. Okay, if r is positive, then this term will keep on increasing, where if r is negative, then this term will die down and it will approach to 0. Okay, so from this what I can say, is if r is greater than 0, then eta will keep on increasing, which means the deviation is keep on increasing, so it's a unstable. Okay, if r is negative, then eta will die down to 0, which means the deviation is die down to 0. So in that case it's stable. Okay, now what if r is equal to 0? What will happen if r is equal to 0? If r is equal to 0, then this assumption is not valid. Okay, if r is equal to 0, which means f prime of x star is equal to 0, at that time if you see this equation, eta dot is equal to this term, which is 0, plus this term. Okay, here we have omitted this term because compared to this term this is small, right? But at this case, when r is equal to 0, this is doesn't matter how small this term is, this is going to be greater than this term, right? So we cannot ignore the higher order terms in that case. Okay, so the stability depends on the higher order term. Okay, so this linear stability analysis is valid only for these two cases, and for this case we have to rely on these higher order terms. Okay, so that's the conclusion of this linear. Okay, not the conclusion, we will see some examples. Okay, so one of the first example we have used is x dot is equal to sin x, right? And for this, what are the fixed points? The fixed points x star is equal to n pi, where n is the integer. Okay, so this will go to 0 at these points. Okay, now in order to identify the stability of those, I mean, it doesn't have a single fixed point, it has a lot of fixed points. Okay, and what about the stability of the fixed points? What is f prime of x, which is cos of x, right? So in that case, what is f prime of x star, which is cos of n pi? So that's what x star is, right? And this will be equal to 1 if n is even, right? Even, and equal to -1 if n is odd. Okay, so when n is odd, it's -1. If it's -1, then at that fixed point, that fixed point is a stable fixed point, and if when n is even, then f prime of x star is positive, so that fixed point is a unstable fixed point. That we could see in our example as well, right? When n is equal to 0, then we observe that as an unstable fixed point, unstable, right? And when n is equal to 1, the fixed point, which is pi, at that time it was stable, right? So it was stable, so we could identify the solution using this linear stability analysis as well. Okay, and in this book Strogatz, there's another example which is a logistic equation. In that logistic equation, we have identified two fixed points, and you could use this method to classify what fixed point is stable and what fixed point is unstable. Okay, you could check this example. Okay, but we have seen that there is a problem with the with this analysis, right? So we'll see an example which will provide the problem. So one one example is x dot is equal to minus x cube. Okay, let's see, x dot is equal to minus x cube. So when x dot is equal to minus x cube, minus x cube, the fixed points are, actually there is only one fixed point, which is 0. Okay, so that point, what about f prime of x star, which is minus 3 x prime square, and we know what is x star square, we know what is x star, which is 0. So here it's 0, our r value is 0, right? So in that case I cannot say whether the solution is stable or unstable. I have to rely only on the graphical approach. Okay, but at this moment let's see whether it's stable or unstable by using the graphical approach. Okay, let's say it's minus cube, right? So now this is the graph, and from this graph I could say when the x is negative, then x dot is positive, so x is going to increase and it's going to approach to this fixed point. When x is positive, then x dot is negative, so it's going to approach towards the fixed point as well. So in this case it's a stable fixed point. Okay, so let's see another example where the first derivative at the fixed point will go to 0, which is x dot is equal to x cube. Okay, at that time if you see when x is equal to x is negative, x dot is also negative, so x will decrease, which means it will go away from the fixed point. At the same time, if when x is positive, x dot is positive, so it will again go away from this fixed point. Okay, so for this case this is a stable fixed point. So what you have to understand is when this f prime of x star goes to 0, it is difficult to classify whether it's stable or unstable, because it could either be stable or unstable. So that's the example we have seen here. Okay, but there's one more case that's an interesting case, which is this one. Okay, y is equal to x square. Even here if you check, f prime of x star will be 0. Okay, if you see here, when x is equal to when x is negative, okay, x dot is positive, so it will approach towards the fixed point. But when x is positive, x star is still positive, so it will increase and go away from the fixed point. So in this region it's approaching the fixed point, but in this region it's going away from the fixed point. So it's neither stable nor unstable. Okay, so therefore we call this as half stable. Okay, we call this as half stable, and to denote the half stable, so let's say this is a minus x cube. So in order to represent stable, we represent that fixed point in this manner, and if it's unstable, we represent the fixed point in this manner, right? Yeah, in this manner. And for half stable, we represent it in this manner. Okay, and in the fourth example, x dot is equal to 0, which means doesn't matter whatever the x is, it's going to stay. There is no there's not going to be any change in x dot. Okay, that's what it is. And if we draw it, if we use graphical approach, and we will represent it like this, which means all these points are fixed points. Okay, so that's all about the linear stability analysis. In the next video we will discuss about existence and uniqueness. Thank you.